Okay, I think we can get started. So, welcome everybody. I'm going to talk about what we aim to do with these sessions first, and then we'll dive into today's topic. I think you guys can already see what the topic is. We're basically going to be doing an introduction to Kubernetes today, but this is a series of talks, demos that I want to build with input from the engineering team. So what it is essentially um, not a one-on-one introduction for you guys. It is basically demos and technology exploration around the technologies we use day in and day out in our day-to-day work, solving problems that we encounter day in, day out, and sort of demonstrating those problems to the wider audience in the company. So the idea behind these talks is to, one, show you guys the cool technologies we're using, maybe not on your project, but elsewhere in the company, sort of evangelize the use of these solutions among your teams. So you guys can go ahead and think about how you could possibly integrate this um, into your projects, or maybe you could see some synergy into seeing how it could possibly make life better for your customer. So this is the first in the series. I don't think it's going to take longer than about 30 minutes for me to talk through this slide deck that I have, and then we can sort of, open up to the wider forum, have you guys ask any questions that you need, and sort of have you guys then suggest topics for future explorations that we may have. Currently, the plan is to have this about once a month. Depending on the amount of topics we have and how many we want to cover, depending on the urgency, I will probably work to see if we can maybe make it a weekly thing or make it a fortnightly thing. We'll see. We'll see how it goes. So this is the first one that we're going to do. What we're going to be looking at today is, since a lot of you people, a lot of the engineering team is interested in Kubernetes and may not have the opportunity to work on Kubernetes, and looking at the adoption of Kubernetes right now, I think it's necessary for everybody to at least have an understanding of how Kubernetes works at a high level. There will be future LTTs where we talk about, deep dive into various aspects, and one of them that we're going to be looking at for sure is deep diving into the networking aspect, which is where something both Gade, Varke, and Vinay also, to a certain extent, have pointed out that people would be interested in looking at something like this. So today we're going to look at a primer on what Kubernetes is, what are the major moving parts in the architecture. So here's what we'll be covering as a guide for you guys. What we'll be covering is, at a high level, we'll be talking about the Kubernetes architecture. We'll be looking at the role of etcd in Kubernetes, which is basically the central data store in Kubernetes. We'll also be looking at the Kube API Server, which is basically an interface to everything that happens in the cluster. It's the main orchestrator, so as to speak. We'll also look at controller managers. So when you look at when you think of controller managers, they are the sort of pieces of technology within the cluster that add functionality to the cluster, and we'll look in seeing how they operate and how they actually behave. The KubeScheduler is one of the major moving parts of the cluster. It is the one that actually determines where workloads execute and how they execute. And sort of that is, we'll look at the internals of how it does this and how it ranks the nodes and how it actually selects which would be the most appropriate place to place a workload in this presentation itself. And then moving on from the KubeScheduler, we'll go on to the worker nodes, where we look at the Kubelet and the Kube-proxy and what are their roles within the cluster. So let's start by looking at the architecture of the cluster. Now, when we talk about a Kubernetes cluster, there are kind of two distinct roles that are played in the cluster. One is you have a master node, and the second, you have a set of worker nodes. At the very minimum, you need one master node to have a working cluster. But if you want, you can run multiple master nodes in a high availability fashion, and have sort of them cooperate to manage the cluster. Almost all configuration and settings flow from the master to the worker nodes. So the worker nodes are just do what the master or the control plane tells them to do. So the master is you can say, the brains of the operation here. And in the master, we run etcd, we run the Kube API Server, we run the Kube Controller Managers, and the KubeScheduler. So these are the components of the control plane that run on the master. Now, it's not mandatory to run etcd within the cluster, but it's usually bundled and it's run as part of the master. But you can definitely run etcd outside and have the master servers connect to an etcd cluster that you manage outside. On the worker node side of things, there are three major components. One is the Kubelet, one is the Kube-proxy, and the third is the container runtime engine. So from a worker node perspective, it's fairly simple. They only deal in pods. The Kubelet, you can think of it as the captain of your worker node. It's the one that controls everything that happens with the worker node. It does what the API server tells it to do. The Kube-proxy is your traffic manager. It's the one that is responsible for routing traffic across. And we'll look at all of these pieces in detail as we go along in the presentation. The container runtime engine is something that Kubernetes doesn't bundle itself now. It is something that is shipped separately, so you have to install this separately. You can choose what container runtime engine you want. As long as it's suitable with the CRI, it will work with the Kubelet. So the Kubelet will connect to it, the Kubelet will control it, the Kubelet will tell to start and stop pods, and it will gather status from it to send to the API server. So now let's start looking at the control plane components. And the first and one of the most important that we'll look at is etcd. So what is etcd when we talk about it? Etcd is actually at its heart a key value store. It is distributed and it's reliable, which is one of the reasons why it was adopted to use in Kubernetes. So when we say when it's distributed, you can run it as a cluster. So you can run multiple copies of it. They will do a leader election. And basically the leader will be the one who's responsible for all the writes and then propagating those writes to all the followers. And when we say it's a key value store, we mean that it doesn't store data like a normal relational database would. As in a table, you have tables with columns and data inside those columns. The key value stores work differently. They work on terms of defining a key, and you can query on that key to get the value stored against that key. Okay, so the API server is the one that is actually writing new information to etcd. Every other component is the one that reads information from here or watches data in etcd for changes and then reacts. So let's look at the API server next. Here, I've sort of demonstrated what would happen during one communication cycle with an API server. But what is the API server within Kubernetes? The API server for Kubernetes is essentially the external and internal interface for any interaction to happen with Kubernetes. So if you want to change any configuration, you want to update any configuration, you want to fetch any data, you will talk to the API server. So if the API server is down in your cluster, you will not be able to make any configuration changes in the cluster. You will not be able to create new pods, deployments. You won't be able to create anything in the cluster. So what are the major functions of the Kube API server? The Kube API server exists to authenticate users. It validates requests. So when I say authenticate users, it actually checks if the user has the right credentials. It checks if the user has the right permissions to do the operation he's requesting. It validates the request. So is the request a valid request? Does it have all the necessary fields to perform the operation? Are those fields have the right data in them? So it validates them. And if it's a GET request, it fetches the data from etcd and passes it along. If it is a write request, it will update etcd with the data. So here what we are trying to do is we're trying to create a pod in the default namespace. So the user sent a request, a curl request to the API server. The API server has gone ahead and updated etcd saying there's a new pod being created. And this is where the Kubescheduler is keeping a watch on the pods. It notices that there's a pod being created. It doesn't have a node assigned. So what it does is it goes ahead, looks at the worker nodes, looks at the, does its algorithm, it runs through to find and select the best available node to run this on, and it lets the API server know, hey, this pod you just created, I think you should run it on worker node 1. And then the API server actually goes ahead and lets the kubelet know, saying, hey, kubelet, here's the configuration for this pod I want you to run. And the kubelet then actually starts up that container on whatever you're running as your runtime engine, the container runtime engine, which could be Docker or Rocket. It just starts up this container, and then it actually sends pod status back to the API server that the container is creating, the container is running, this is its health, this is the resources it's using, and all of that then starts appearing when you run your kubectl commands. Now we look at how the Kubescheduler actually does the ranking and filtering of these nodes to select the best one a little later. But before that, let's look at a pretty interesting piece of technology within the control plane, which is called controllers. So, like I said in the introduction, the controllers are the ones that sort of add functionality to the cluster. So we'll, I think it's best explained by using an example. And let's use the example of a replication controller. So whenever you create a replica set within Kubernetes, and a replica set is just basically an object that says, I need to have X pods running, X copies of this pod running, and the configuration of that pod. So what the replication controller does is it watches the status of all the pods. And if it notices a difference in the number of running pods versus the number of requested pods, so let's just say, we have a situation where we have a 4-node cluster and one node dies. And we had pods that are under this replication controller that were controlled by this replication controller underneath in that node. So what happens now is the replication controller notices that, hey, one of my pods has gone away, or two of my pods have gone away. And then what it does is it sends a request to the Kube API server and says, please start 2 new pods with this configuration. And the Kube API server goes and lets the kubelets know after obviously the Kubescheduler has told it where to place them. It lets the kubelets on those nodes know, hey, please start up 2 copies of this. So I have mentioned a couple of time periods there. So usually what happens when a node goes away, the node health checks happen once every 5 seconds. The grace period a node gets is about 40 seconds. So it can have a maximum of 40 seconds between 2 successful health checks, so we don't disrupt traffic too much. And we have a pod eviction timer. So if a node is not available for more than 5 minutes, it's not ready, pods from them will be evicted and they'll start to run on other nodes in the cluster. So this is the sort of timeline that things would happen. If a node failed a health check, we'd wait 40 seconds before marking it not ready. And if it still doesn't come back within a 5-minute window, we'll kill that node, or rather we'll mark it as unavailable, non-schedulable, and then move the workloads that were on it to other nodes. And all this happens because the replication controller is the one that actually watches these nodes, watches these pods underneath it, and then sees whether there are any differences between the number of pods that are requested and the number of pods that are actually running per deployment. And there are many controllers like this that run on the Kube controller, in the Kube system namespace. So we have stuff that controls deployments, namespaces, cron jobs. We have for persistent volumes. We have for replica sets, replication controllers. So the cron job controller's job is basically every time a schedule is hit, a schedule is active, it will start up the necessary pods to run for that schedule. So it's just like your normal cron that runs on your Unix machines. Every time that time stamp is hit, it starts up the needed pod, executes the job, and then it shuts them down. And all of these controllers, they run under one pod called a Kube Controller Manager. And you can actually select which controllers you want running, which controllers you want to disable when you actually set up your master. So you can say, you know what, I'm never going to use persistent volumes in this cluster. You can actually shut those controllers down if you want to reduce the resource usage on your master. Now, let's look at one of my favorite topics within Kubernetes, which is the Kubescheduler. So like I said earlier, KubeScheduler is the one, it's the piece of technology that is responsible for picking the best node to schedule the workload on. Now, you must be thinking about how does it do this? So it does this in sort of two steps. The first step is a filtering process where it looks at what the pod is asking for, whether it has any special considerations on it. And then once it has a set of compatible nodes or candidates from the pool that it can actually put the workload on, it tries to rank them and gives a priority to the ones with more free resources. So basically to maximize the available resources in the cluster. So now when I say that, it sounds a bit abstract, but let's take a concrete example and look at it. So we're trying to run a container here that's requesting for 10 CPU. We have a 4-node cluster. And on the first two nodes, node 1 and node 2, we have only 4 CPU available. On node 3, we have 12. And on node 4, we have 16 CPU available. So what this means is when we filter the nodes for saying the resource requirements require 10 CPU, node 1 and node 2 go away completely. So we're not even going to consider them as candidates for where we can schedule this pod on, simply because there are node 3 and node 4 which have the available CPU that this pod is asking for. And then what it's going to do as a second step, it's going to rank these two nodes. So we're only going on one axis, which is the CPU axis here for simplicity, but there are multiple things it considers. But here, if it places it on node 3, what happens is then the available CPU on node 3 goes down to just 2. So it may be harder to place workloads there when you only have 2 available CPU. But if you place it on node 4, you will have 6 CPU available. And that's a much bigger resource pool that will be available to other workloads in the cluster. So the Kubescheduler will make a decision and say, node 4 is the better one to place it at. Now, this is a very simple example, but there are ways you can actually control and influence the decision that the Kubescheduler makes. And we'll look at a few advanced topics of that in a little bit. Okay, just 1 minute, there's somebody waiting in the lobby. Okay. So now let's look at some advanced topics in this Kubescheduler. So the Kubescheduler, one of the things it does take into consideration when you're trying to schedule, like we looked in the example, is it looks at resource requirements and limits. So in the pod, when you define a pod, you can actually set the resources that the pod requires. You can set a resource requirement, and you can set a limit. So you can grow to X amount. So if you set just a limit, then that is the request. The request is equal to the limit, and Kubernetes will allocate that much for that pod. But if you set a lower request and a slightly larger limit, it'll try to accommodate it based on the request. And not everybody will be hitting the limit at the same time. So you'll try to accommodate in that sense. When we talk about taints and tolerations. So taints and tolerations is a way for nodes to repel certain workloads. So when I say repel certain workloads, this is used in making sure that, like, one place it's always used is to make sure that none of the user-defined workloads run on the control plane. So all the control plane nodes have a taint. And what that taint does is, unless a pod that wants to run there has a toleration for that taint, it will not get scheduled on that node. Now, just because a node has a taint and a pod has a toleration for that taint doesn't mean that they will get scheduled on that node always. That's one thing to remember. It's just that if you have a toleration for a taint, that tainted node gets into the pool of available nodes for you to schedule on. The scheduler will still rank your available nodes and see which one would be the best fit for this workload. So you could have a tainted node and a toleration on a pod, but that pod may not get scheduled on the tainted node. It's just that it is considered to be scheduled. And if it has free resources, it'll almost always go there, but it's one thing to remember when you're setting stuff up like this. So that is one way for the nodes to repel workloads. Another way to make sure there's a stronger bond between a workload and a set of nodes is to set up node selectors or affinity for a node. What you can do is you can make sure that if, let's just say, for example, you have a pod that has certain hardware requirements. And when I say we're talking about hardware requirements, let's say it runs a graphical, it runs some data science thing, it needs access to the GPU. And there are only like 2 or 3 nodes in your cluster that actually have a GPU attached. What you can do is you can label those nodes. And when you are creating these pods, you can say that these pods always need to run on a node that has this label. So when the KubeScheduler filters these nodes, your available nodes in the cluster, when it's considering scheduling this pod, what it'll do is it'll only select those nodes that have this label or this selector attached to it. And then it'll only consider those, rank them, and then schedule your workload on them. So that's a fairly powerful way that you can influence the scheduling decisions that the KubeScheduler makes. And if you don't like the way the KubeScheduler works, you can definitely write your own KubeScheduler and run it in the cluster. So this is a completely user replaceable piece that if you see that there's a functionality that the default KubeScheduler doesn't have, you can enhance the KubeScheduler, build an image, and completely run a custom KubeScheduler within your cluster and have that function as the primary scheduling part of your cluster. I wouldn't recommend it. I would recommend running 2, and then you can have a certain set of pods that actually use your custom scheduler on it. You can even run multiple kinds of schedulers and decide which pods want to use which schedulers in the pod configuration. So it's a very powerful way of controlling where workloads go, and it's a very flexible way of doing it. The default options out of the box are pretty flexible, and if they don't work for you, Kubernetes just lets you replace that with a custom implementation that you write that you can use. So now we've looked at all the major components in the control plane. As the next step, let's look at the 2 components that Kubernetes runs on the worker nodes. So when we talk of the kubelet, I put a little captain symbol there. I want you to think of the kubelet as the captain of the worker node. So it's the one that is actually in charge of all the containers in that worker node. So everything that runs in this worker node runs because the kubelet has started it. So it takes commands from the Kube API server, but it is the one who actually starts up the container, tells Docker to run a container, to kill a container, and it only operates on containers. It only understands pods. That is the sort of level of understanding it has. It doesn't understand deployments. It doesn't understand replica sets. It doesn't understand the higher level abstractions. The only thing it understands is containers, and it exercises the Docker runtime engine or your Rocket container engine to actually start up the containers and then start reporting status back to the API server. So it is also the one that actually registers itself with the API server to tell it, hey, I'm available to run workloads. This is what I provide to the cluster, this many CPU, this much memory, this much hard disk, and this is the class of my service. And if you run actually the command kubectl describe node and the node name, you will see the wealth of information that is provided. It even lets the API server know if it has pressure on its memory or CPU or hard disk. It's whether those resources are being churned or being used a lot. And the scheduler can then use those parameters to actually decide and rank which would be the best node to actually select for running a new workload, maybe. And it also monitors the node. So it's responsible for the health checks that go to the API server. It is responsible for all the containers that run there, reporting their status back to the API server. So when you run a kubectl get pods, that is actually from the information compiled from what the kubelet is actually sending, what all the kubelets in the cluster are actually sending to the API server. So we run one kubelet per node. Okay. So this is the last slide for kind of today, and it's a fairly important one, and we'll be deep diving into this in a future LTT. This is the Kube-proxy. So to give you all a brief idea of how networking works in Kubernetes. So Kubernetes expects a flat address space. So when I say what I mean by a flat address space is basically anything in that address space should be able to talk to something else in that address space without the need for translation. So without the need for a NAT gateway in between, without the need for translating from one network to another. So it's basically one block of CIDR that Kubernetes expects all the pods to be placed into. So now earlier, Kubernetes expected you to set this network up yourself. But now in newer versions of Kubernetes, you have a CNI plugin containing a container network interface plugin. And there are multiple plugins available. There's one which works specialized for AWS VPCs. There's one that works specialized for just creating a generic overlay network like Flannel or Calico. There are ones that implement network policies that let you actually control to a deep level the kind of traffic that is happening between your pods. Because Kubernetes makes no distinction that any pod can talk to any other pod in the same namespace without NAT. Same thing with different namespaces too. A pod can talk across namespaces based on the IP address, no restrictions. And we may want to restrict that. And that's something we will get to in a future version of this talk. So let's sort of take this with an example. So in this example, we have a standard two-tier application. The blue node is the web application layer, and the green node is the database that it connects to get its data from. So what is happening here is the blue node can talk to the green node by just using its IP address. So 10.32.0.15, and it'll get a response from that pod. But now what happens is we can't guarantee that pod that is started will always have this IP address, because the IP address is given to the pod from the pod network, and it can be anything, any free address. We don't control it. The CNI plugin does. So what happens here is, how is the web service actually going to be able to talk to this database pod? So Kubernetes has an abstraction called a service. And there are different kinds of services, and we will go into those a little more in detail in a different lecture. But what this service is essentially an abstraction which acts as a proxy, so that it has its own IP address, and it exposes a port that you can send traffic to, and it basically proxies this traffic down to the actual node, the pod in question. So here we're calling it service DB. So all the web service needs to know is my DB is available at my database service is available at TCP DB : if it's MySQL 3306, and the service is the one that will actually take care of sending the traffic across. Now, I did say the service is the one that will take care of it, but not actually. The service is the one. Is just an abstraction. It's just a configuration object within Kubernetes. The Kube-proxy is the actual component that goes in, looks at the service configuration, and then creates the necessary IP table rules or configures the necessary networks within each host, within each node in the cluster, and then allows this traffic to flow this way. So there is one service that's fairly interesting called a node port service. So when you have a node port service, what it does is this actually exposes a port on the IP address or the host IP address of the node. So you can ping each node's IP address and that port, and traffic will reach your pod, even if that pod is not running on that node. So you can, if you have a 10 node cluster, you can take all 10 IP addresses with the same port, and traffic will reach your desired pod. And this is possible because the Kube-proxy is the one that actually goes ahead and creates the necessary configuration to allow the traffic to hop across the nodes and get to the right pod. So at a high level, this is sort of the major moving pieces within a cluster. We've looked at them at a fairly high level, and there will be stuff we will dive into in detail, like networking in Kubernetes. We'll also look at security in Kubernetes, how RBAC works, and what is a cluster role, what is role, how access is controlled. We will even look at how you actually connect to the cluster. What are the security? Why do we need PKI when we actually connect to the cluster? Why do we need a certificate or signing authority, and all of that? How the service accounts work? All of these things are sort of coming up, but I wanted everybody to have this as their basic knowledge before we start talking about any advanced topics. So with that, this kind of ends my presentation that I had for today. I think we have I'd say about 30 minutes left. So I'm going to open the floor up to any questions anybody may have. If you want to go back and talk about something in more detail, or you have questions about something specific we talked about today, please feel free to open up and let's talk about it. Did I do such a good job explaining that nobody has any questions?
So, Colvin, let me ask you.
Sure, Jiten, go ahead.
Do you have? I know. Any other favorite pointers you have where we could pull up the information you have? I know Kubernetes.io, but any other pointers where? Like the how
So
to's,
basically, you want to know,
yes,
yeah,
like the how to's is the go-to
okay,
place. Any other pointers you have, your favorite ones? Yes.
yeah. So there is, if you really want to learn about the internals of Kubernetes, right? There's a guy on GitHub called Kelsey Hightower, and he has a GitHub repository called Kubernetes the Hard Way. So now there are multiple ways you can install Kubernetes. There's K8s, there's EKS, and everything. But And there's kubeadm also, which is what the documentation talks about when you want to install Kubernetes and get it up and running. But Kubernetes the hard way actually gets you to set up every step manually. So the configuration of the API server, how do you set it up? The configuration of etcd, how do you set it up so that it talks to the API server properly? The generation of all the certificates that happen within the cluster. So that is definitely something you can follow along. It's a great guide if you actually want to learn how the internals of Kubernetes function, how it communicates with each other, how to actually fire how the nodes actually join the cluster. So from a cluster administration point of view, that is a great way to get some really good knowledge. And it takes a good I'd say when I did it Kubernetes the hard way, I did it when it was I think at version 112 or 113, maybe 114, I think. And it took me a good 3 or 4 days to actually get a working cluster. So I'd suggest everybody take a look at that. That's definitely a resource that I would recommend for anybody who wants to learn more about the internals of it. Just be aware that it is fairly important.
Thank you.
Okay, any more questions?
Hi, Colvin.
Hey.
Okay, so first of all, thanks for the information that you shared. What are the pre-requirements for the next session whenever you are planning, so that we will not miss some information. Like we will be
So
kind of
yeah.
prepared
So
a
the
bit.
so the idea behind these sessions is basically to grow your knowledge in a structured fashion, right? So which is why we started with this basic one, which is just a basic introduction to Kubernetes, what the major moving pieces are, so that when we go into deep dive into a few other topics, you won't be completely lost. I wouldn't suggest you guys come prepared for any of these, because these are going to get way more interactive in the future. So we're actually going to have demos that I will live code against. I will take suggestions from you guys about how we should try to fix this problem that we have. We will probably build out architectures ourselves. We will break it. We will see what the problems we face while doing it are. So I would suggest, if you have a basic grounding in what we're going to be talking about, should be good enough. But I don't think there will be something specific, unless it's a deep dive into a certain technology. Then obviously we will need some basic knowledge in that tech.
Colin, Akash here. I have one question.
Yeah. Hi, Akash.
Yeah. So we use core DNS and Kube DNS. We can use one of them.
Yep.
I just wanted to understand the integration between this core DNS or Kube DNS with a Kube-proxy. Means how it works.
Yeah. So basically, when we talk about DNS, right? So Kube DNS is something that's going away. It's going to be deprecated soon. Core DNS is the sort of way forward. So the way DNS works in the cluster is basically it translates DNS names to IP addresses, right? It just like it works in the normal world. Like you type google.com, it actually in the background, you get a TCP IP connection to an IP and your browser renders the page. So, but that is how it works in the cluster. So for Kube-proxy is the one that actually, I don't think it's the one that writes the addresses into Kube DNS. It's something that I will have to go back and check. But basically what happens is to address stuff in the cluster, there is a certain domain that you use, which is cluster.local. And you add on the svc.cluster.local is for services, pods.cluster.local is for pods. So you can have a pod name.pod.cluster.local and address it that way. So basically, the API server is the one that creates these DNS entries when needed in Kube DNS. And then anybody can go in and look up these DNS names and get an IP address for them. And it's mainly used for service-to-service communication. but you can definitely use it for pods. You can definitely use it for anything that is addressable in the cluster.
Okay, okay, okay. So my understanding was Kube-proxy is the one who creates the DNS entries, and I think Kube DNS or the core DNS resolves it. But yeah,
Yes, so core DNS is your DNS server.
right.
So Kube-proxy does more than just create that DNS address. Kube-proxy also creates the routing rules on each node. So I didn't want to introduce the DNS part because it gets a bit more complicated. But basically what happens is, like, let's say when you have a node port service, right? You have a 10 node cluster and your pod is actually running on node 1. So when you connect to, let's say, node 7's IP address and the same node port, which let's say, for example, is 33804, right? Kube-proxy is the one that actually redirects the traffic. The traffic is going to come to 3304 of node 7, but the traffic is going to be redirected to node 1 because that's where the pod actually is.
Correct.
And Kube-proxy is the one that actually sets up the IP table rules to say, okay, if traffic is coming in on this port, I need to forward that traffic to this IP address and this port. And then it actually goes through. So it's the one that, you can think of it as the proxy gateway, so as to speak, in the cluster that sets up all the IP table rules so that communication is clear. So if there's a new service created, all the Kube-proxies get the service IP addresses. Because the service has its own IP address, the Kube DNS will know what that IP address is, and it actually then goes ahead and creates the necessary IP table rules to forward packets to the right place.
Okay, got it. Thank you.
Addition to this question, Kovin, hi, this is Shrikar.
Yeah.
In case of on-premises installation, then what's the use of network add-ons like Calico Wave, like that? Because Kube-proxy is doing the job, so what's the use?
Yes. So earlier, what used to happen was Kube-proxy was there, and it did a lot more work. But when you have a high traffic, when you have a lot of pods being created, right, and adding more functionality was making the Kube-proxy way more complicated. So what they did was they sort of split it up, and now you have a CNI interface, which is the container networking interface. So what this defines is basically what the network for the pod should look like, how traffic should flow between pods. So there's an IP address place, there's a separate CIDR for the pods, and how traffic enters the pods, how the pods get an IP address. Everything is controlled by this Calico, Flannel, Weave. All of that is controlled by that. So like, let's say you want to run your pods in a VPC, in an AWS VPC. There is a CNI for that. So that CNI will actually give you IP addresses from that VPC and let you run your pods in that VPC. So for anything else in the VPC, it's like they're talking to an EC2 machine instead of an actual pod. So this is what the sort of CNI plugin lets you do. So you can think of the Kube-proxy as managing the internal communication of the cluster. So it's the one that actually does the setup for the internal communication. And what the CNI does is it looks at the pod-to-pod communication. So it's basically, you can set up, so I don't know if you know about network policies. So network policies are rules that you can set on a pod and allow you to allow ingress from only certain pods, allow egress to only certain pods from that node, from that pod, so as to speak. So all of those implementations are controlled by the CNI. So you can have a CNI that gets very, very complicated very fast because you can then do traffic shaping. You can do security analysis on the traffic that's going between the pods. And putting all of that in the Kube-proxy was getting too complicated. So they broke that apart, let the Kube-proxy handle the sort of internal configuration that is needed for the pods to communicate with each other, and all of these sort of higher level network functions where we want to do traffic shaping, we want to do network analysis, we want to make sure that traffic is flowing, or we want to block certain traffic. All of that functionality has been encapsulated into the CNI plugins.
Yeah, thanks a lot.
Okay, cool. Are there any more questions? No? Okay. Okay, cool. Thank you guys for taking time out from your day, attending this lecture for the first time. Keep an eye for more down the road. We're trying to make it a monthly thing. Akash, do you have another question?
No, actually.
Okay. No, you unmute. I saw you unmute, so I thought you had another question. But well, thank you for joining. Thank you for asking questions too. And sort of next one will we announce in advance what we're looking into, and you will also see a sort of poll or a place where you can suggest topics coming up. This is something we wanted to do, wanted to get the ball rolling with it, but definitely we want your input on where this goes. We want this to be useful for you guys, and sort of take the information shared here and use it in your day-to-day job. So you guys should be the driving force behind it, and hopefully I will also learn something new. Definitely one thing I want to look at is how which is the thing that actually writes the DNS entries. I think it's the API server, but I'm not sure yet whether it's like Akash said, whether it's the Kube-proxy or the DNS server. I'm going to go back and read about it. So it's probably something that I will learn today too out of this exercise that I didn't know when I started this presentation. So hopefully, everybody learns something out of what we're trying to do. Okay, cool. Thank you, everyone. We're going to end this meeting a little early, give you guys 15 minutes back in your day, and we'll see you in the next one. Have a great day, everyone.
Thank you.
Thank you, Colin. It was very informative.
Right. Thank you. I'm glad you guys found it informative. Thank you.
Thank you.